Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we will discuss about what is CPU scheduling and the basic concepts involved in the CPU scheduling such as CPU I/O burst cycle, the scheduler, the preemptive scheduling issues and the dispatcher. In a single processor system, only one CPU can allotted a one process at a time, and the other might wait for the CPU that the process should be completed and it can be transferred the allocation of the CPU to the next process. At that time, the CPU just sits idle while waiting for the next process. In a multi-programming environment, we must objectify to use that same or other several processes to be run at the CPU concurrently. It is very simple idea. A process is executed until it has to wait for some I/O completion or I/O request or any other request to block. When the CPU is waiting for the process, then in a single processor system, it has to be idle as we have already told. Now the waiting time is wasted and the CPU is not doing any proper work. Now in a multi-programming environment, we use this time productively. While a process is waiting for the CPU, then the CPU allocation is takes from that process and is given to another process. By this way, we can utilize the CPU time efficiently and reliably. In this way, the cycle continues, and while waiting for the process of the CPU allocation, it snatches it from that process and gives it to another process. Now, the CPU scheduling is a fundamental operation of the operating system, as all resources should be scheduled before use, and CPU time is an important resource available to the computer system. So the scheduling a CPU is of the central importance of the operating system. So the basic concepts involved in a CPU scheduling we will discuss today. The first one is the CPU I/O burst cycle. The CPU scheduling can be done in a good way by an observed property of the processor. A process can execute in two ways, the CPU execution and the I/O wait. When the CPU execution is done, a process begin its execution. After that, it is waiting for an I/O to complete. For the I/O completion, it again gets a CPU burst. Again, I/O burst is given to him. And finally, this cycle continues, and at last, the CPU burst is executed to terminate the process's execution. Now in this way, the cycle continues and we can choose among the good selection of CPU burst and I/O burst balanced process to be get into the CPU scheduling information. The duration of CPU burst are measured extensively, and we can plot this CPU burst I/O time incompletion in a graph. This graph is characterizes exponentially or hyper-exponentially, where a large number of short CPU time bursts is allocated, whereas a shorter or smaller number of short CPU time bursts is also allocated. The I/O bound processes are having frequent switches between the short CPU bursts, whereas the CPU bound time are allocated with longer CPU bursts and in a fewer number. Now this distribution can be important among scheduling the CPU, and the algorithm can be chosen according to that. The next one is the CPU scheduler. While a process is waiting for an I/O to complete, it must be chosen that another process from the ready queue that is to be ready to execute it and waiting in a pool. This can be done by a CPU scheduler or a short-term scheduler. It actually selects a process from that pool and allocates the CPU to that process. We should note that the priority queue or the ready queue is not always in a FIFO order. The ready queue can be any of these: FIFO queue, a tree, a priority queue, or a normal unordered linked list. Now choosing from this ready queue is generally happen about the chaining of the processes that are waiting to run on the CPU. The records in the CPU are the process control blocks of the processes. The next one is the concerned issues of the preemptive scheduling. CPU can switch among the processes among these four options. The first one, when a process is going from the running state to the waiting state as it terminates, or by the wait system call where a parent is waiting for the child to terminate its function. The next function or the next option is when the consumer process is gone from the running state to the waiting state during an IO completion or IO wait. Now the next option is the process is gone from the ready state to the waiting state due to the interruption occurs. And the fourth option is when a process terminates. Now for the 1 and 4 option, there is no choice of the CPU scheduling. If a process is exiting, then another process should execute from that thread pool or ready queue. Now choice exists when there is under 2 and 3 option, where the states are going from the waiting to the running state. Now we can choose that which processes should run depending on the preemptive scheduling. When no choices are there, the non-preemptive or cooperative scheduling operates, and if choices are there, preemptive scheduling operates. Now in non-preemptive or cooperative scheduling, the process will execute it and allocated a CPU, keeps the CPU until it releases the CPU by terminating or waiting for an IO by giving it a wait call. Now this cooperating process scheduling was implemented as Windows 3.x. Windows 95 and subsequent firmware versions used is the preemptive scheduling. The Macintosh versions of Mac OS IOX use this preemptive scheduling, and the previous versions were lying on this non-preemptive or cooperative scheduling. Now this cooperative scheduling can run on certain hardware only because it doesn't need any special hardware to provide support to the preemptive scheduling. The preemptive scheduling happens when one process can be preempted with another process depending on various situations. Now the first issue during the preemptive scheduling is the rest condition. It happens when two or more processes that are preempting when sharing the data. For example, if a process is updating a data and in the meanwhile it is preempted by another process which is then using the same data, which is in an inconsistent state. So there the rest condition appears. Preemptive scheduling will also affect the design of the operating system kernel. Now when system process call is happening, then the kernel is busy with behalf of the process by blocking the system call. Now if there is a preemptive scheduling, now kernel is updating a data structure or modifying the data, then what happens if the kernel is updating the same data structure that is being preempted? So the problem is solved by the other operating systems like Linux and Windows is by providing a unit IO block before context switching or by waiting for the system call to complete its execution. This way, kernel can provide a simple structure and it can avoid the unnecessary getting up of modifying the shared inconsistent data. But the kernel execution model is very poor as in the runtime execution system of a real-time system. In this real-time system, the processes must complete its execution within a given time frame. Because interrupts can be definition occurs at any time and the operating system cannot ignore it always. By default, the operating system should always accept an interrupt, otherwise input lost data or the output can be overwritten. Now this interrupt can be handled by the operating system with the scheduling also. The section of code that is affected by these interrupts must be guarded from simultaneous use. Now the code can be provided an avoidance of the concurrent use by the scheduling information, and the scheduling can be programmed very carefully. As we cannot provide avoidance of the acceptance of interrupts, so we can put by disabling the interrupt at the entry of the process and re-enabling the interrupt at the exit of the process. Now the process that supports this disabling of interrupts are very few and it contains a small amount of instructions within them. So these preemptive scheduling issues that needed to be solved between the scheduling information of CPU should be concerned about a balance of CPU and IO burst cycle. The last concept is the dispatcher. Now the dispatcher actually allocates the CPU which to the process from the ready state and ready to be executed. It is a module that is assigned by a short-term scheduler to actually allocate the CPU to a process that selected by the CPU scheduler. Now it provides three functions. It switches the context, it switches the user mode, and it also jumps to a section of code that will restart the program. The dispatcher should be as fast as possible because it happens every time a switch is compulsory between this context. Now the completion of a process and starting of a process, the time between them is known as a dispatch latency. So there should be minimum dispatch latency executed by the dispatcher and followed by the CPU scheduler. That is all for the basic concepts of CPU scheduling. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.